In this video, we're going to be continuing our exploration of counting methods, and we're going to focus on what we call combinations as opposed to permutations. Okay, and so in our last video, we discussed permutations and how we kind of interpreted them. We say when counting the number of permutations for a set, recall that the order in which the elements are arranged, that's important. Okay, so we say when order is not important, we say however, when order is not important, it says then the subsets that we're considering are referred to as combinations. Okay, so we say first of all, what is a combination? What I can tell you is this. We say it is the number of ways that something can happen. Of course, it's a combination. But first thing we want to note here is this. Order doesn't matter, okay? So when we're talking about situations where we need to count and order does not matter, what we're going to be using instead of permutations is combinations. So what I want to do is really just compare and contrast the two methods. We say consider the thought experiment in which we wish to find the total number of possible three-letter combinations that exist for the letters A, B, C, D, and E, okay? And how is this different from using permutations? Well, what I can tell you is this. If order mattered, okay, then what I could tell you is, let's say I chose hypothetically A, B, and C. These were my three letters that I chose out of this bunch up here. What if I were to choose instead A and then C and then B? Would that be different? And I'll tell you what, if order mattered, if order really did matter, then these would be two totally different events, because in the first event we chose A, then B, then C, and the second one we chose A, then C, then B. But what I can tell you is when we're talking about combinations and order doesn't matter, I can actually tell you with utter confidence here. We have BAC, I could choose BC, A, like what if I kept choosing these three same letters here? BCA, I see C, A, B, could choose that here, and we say C, B, A. As a matter of fact, in combinations, what we would say is that all of these are considered to be the same thing. Okay, so the same thing. And the reason why that they are the same thing is because, if you choose A, B, and C here, that's the same thing as if you choose A, B, and C here. If order doesn't matter, you got the same three letters. So in terms of treating this differently from a permutation, well, I'll tell you what, if order did matter, we would say that I have 5 things, and I'm rearranging 3 at a time is what I'm saying. So we would have gotten 5 permute 3, and this comes out to be 5 factorial over 5 minus 3 factorial, which is just this. We say 5 factorial over 2 factorial. The thing I want to point out, at least with this specific case, is this though. How many ways, if I chose A, B, and C, how many ways after that could I rearrange those 3 things? There are 3 things here, so we say 3 factorial, which is all 6 of these ways right here. But the idea here is this. What we need to do is this. Since permutation represents all the ways we could choose 3 letters from 5 letters, and order matters here, then we would say a combination, we're going to write it a little bit differently. We're going to write it this way. We say 5 choosing, or 5 combinations. And so we have the same number for our n here, and we have the same number that we're rearranging. But what we're going to do is this. We're going to take the total number of ways that this can be done, which, by the way, is 5 times 4 times 3 times 2 factorial over 2 factorial. Looks like we get 5 times 4 times 3, so 60 ways to do it. Okay. What we need to do is we need to divide this by 6, because there are also, every time we choose 3 letters, there are 6 ways that I could rearrange those. And if order doesn't matter, we need to divide out all the repeaters. Okay. So essentially, we're still going to do a permutation, okay? We get 5 factorial over 5 minus 3 factorial. All we're going to do is we're going to build in the extra number of ways that this 3 letters could rearrange themselves. We're going to divide those out. So what we say is, well, how many ways exist to rearrange 3 letters? It's 3 factorial, okay? So I'm going to put a 3 factorial in here. What I end up with is instead, this time I get 5 factorial over 2 factorial times 3 factorial. And you'll notice that both of these numbers down here add up to be this top number, which is a unique property of combinations. But instead this time we get 5 times 4 times 3 factorial all over 2 factorial, 3 factorial, which these 3 factorials cancel out, and I get left with 20 on top, okay, over 2, which comes out to be 10. So there's really only 10 ways to choose 3 letters from these 5 letters, whereas if we were doing permutations, there'd be 60 ways. So why is there a sixth of the amount? Because there were 6 ways for me to rearrange these 3 letters after I chose them. So what we're doing is dividing out repeaters. So the difference between permutations, I'll write this down here. We say n objects rearranging r at a time would be n factorial over just n minus r factorial. But when we discuss combinations, we say that it is n choosing r at a time where order doesn't matter. Then we say we still get n factorial over n minus r factorial, but the other amendment we make here is that there's an r factorial. So let's talk about how we could use this to our advantage here. We say a standard poker hand consists of 5 cards dealt from a deck of 52 cards. How many different poker hands are possible then? Well, the first things we want to omit are these. Total number of objects in a deck of cards are 52 cards. And we're taking 5 card combinations. So we say our R in this case is 5, And in this case, does order matter? Now, consider this. If you hold your cards differently in your hand, they're the same hand that you had before. So since order doesn't matter, we're going to do this instead. We're going to say 52 choosing 5 at a time. Okay. So it's 52 choose 5. Let's get used to a few facts here. We say 52 factorial over. Now it says r factorial times n minus r factorial. So our r in this case is 5. We're going to say this is 5 factorial over n, which is 52 minus 5. That thing factorial. So we really get this. 52 factorial over 5 factorial, and this would be 47 factorial. So a few things I want to point out here. First one is this, these two numbers down here, in a combination, we say that this r right here and this n minus r, if you were to add those together, r plus n minus r, the r's cancel out, you just get left with n. Okay. So in other words, these bottom numbers will always add up to the top number here if you're doing combinations. And also this, when we reduce this here, we'd have to say 52 times 51 times 50 times 49 times 48, okay, times 47. Not very good with my 7s and my 8s on this one and my 4s. So we say 5 factorial over 47 factorial. The idea is that we're going to get rid of this here. And we say that this 5 factorial is really 5 times 4 times 3 times 2 times 1. We're going to divide out any common factors that they have with the top here. So we say 5 and 50, this would become a 10. And I don't know what else. So we say 2 would go into 52 26 times. I suppose, 4 would go into 48 12 times. We say 3 would pass into 51 17 times. So I'm going to circle everything we have left over, including things I didn't reduce. And we'll just go find this on a calculator. This is quite a few hands we can make here. But essentially everything on the bottom canceled out. We get 26 times 17 times 10 times 49 right here. And we say times 12. And we end up with 2598960. So 2598960, 5 card hands that we could make in a poker deck. Okay. So again, really quickly here, let's take a look at letter B. It says for a certain experiment, 4 students are randomly selected from a class of 20. So that is, we have 20 students, and we're selecting 4 at a time. Now it says that order doesn't matter here. We're just selecting them. So we would just say that this is 20 choosing 4 at a time. And so this comes out to be, again, let's just kind of quarantine this off here. We say 20 factorial over 4 factorial, and this would have to be a 16 factorial. Writing this out, we would get this. We would say 20 times 19 times 18 times 17 times 16 factorial all over 4 factorial. I'm going to write this as 4 times 3 times 2 times 1 times 16 factorial, because these 16 factorials are going to cancel out. So now we'll start reducing things. We say 4 goes into 20 5 times. 3 goes into 18 6 times. 2 goes into, well, nothing's even up here except for the 6, so we can reduce it again. So we say, all right, well, I think we canceled everything out. So 5 times 19 times 3 times 17. So 5 times 19 times 3 times 17. We end up with this, 4,845 ways. So 4,845 ways. So in our next video, we'll talk about some more exotic combinations.